What if the universe keeps a perfect record of everything that has ever happened? Not in a metaphorical sense, but as a fundamental physical law. Imagine that every star that ever ignited, every planet that cooled, every thought that flickered across your own mind leaves an indelible signature woven into the fabric of reality. This isn't poetry. It is the single most profound and fiercely protected law in the strange world of quantum mechanics. It is a principle of conservation, a promise from the cosmos itself, information, the unique blueprint of any object, the story of what makes it times can never ever be truly destroyed. It can be scrambled, burned, shredded, or scattered to the far corners of the universe. But it can never be erased. The story of the past is always in principle recoverable. This law is the bedrock of our understanding of cause and effect, the anchor that moors the present to the past. For nearly a century, we believed this cosmic promise was unbreakable. And then we looked into the abyss. Before you is a wound in the flesh of space-time. It is a place where all the known rules of physics are pushed to their breaking point and then shattered. We call it a black hole, but that name is far too gentle for what it truly is. It is a gravitational singularity, a point of infinite density shrouded by a one-way door called the event horizon. It is the universe's most perfect prison. Anything that crosses that shimmering, invisible boundary, a star, a planet, a beam of light, a single atom is lost forever. Its journey ends, its story is silenced, its future is singularity. From this cosmic oubliette, there is no escape. There is no appeal. There isn't even a message you can send back. This is the world described by our greatest theory of the large, Albert Einstein's general theory of relativity. It is a masterpiece of mathematical elegance, a sweeping symphony that describes the dance of planets, the waltz of galaxies, and the majestic curving geometry of space and time. For relativity, a black hole is a creature of brutal simplicity. Once it has devoured its meal, it settles, leaving no trace of the complex objects that fell into its grasp. It remembers nothing of their character, their chemistry, their history. All the intricate information that defined a star, its fusion cycles, its elemental composition, its vibrant spectrum of light, is crushed down into just three stark cold numbers: its mass, its spin, and its electric charge. The star's library of information, its cosmic autobiography, has been ripped from the pages of the universe. According to Einstein's beautiful equations, it is simply gone. For decades, this was a curiosity, a mathematical quirk that troubled few. The information was not truly destroyed. Physicists reasoned it was merely hidden, locked away inside the black hole's vault, inaccessible to us on the outside, but still present within. A cosmic secret, perhaps, but not a cosmic crime. But our understanding of reality does not rest on one pillar alone. Confronting the smooth, deterministic universe of Einstein is the frenetic, probabilistic kingdom of the quantum. This is the theory of the very small, the rulebook that governs the ghostly dance of particles, the strange logic of atoms and photons. And this quantum rulebook begins with its most sacred axiomatic law. The story of the universe is never ever lost. Think of a book filled with the most beautiful prose. You can burn that book. You can watch its pages turn to ash, its ink vaporize into smoke. To our eyes, the information, the story is gone. But quantum mechanics insists this is an illusion of scale. If you had a supercomputer powerful enough to track every single atom of ash, every photon of heat, every molecule of gas that drifted away, you could in principle reverse the process. You could reconstruct the precise state of the ink on the page. You could read the story once more. The information wasn't erased, it was just fiendishly rearranged its complexity, encoded in the subtle correlations between billions of scattered particles. It is the ultimate statement of cosmic persistence. What was in some form will always be. And right here at the edge of a black hole, we have a crisis. We have an irresistible force meeting an immovable object. On one side, Einstein's general relativity, our flawless guide to gravity, tells us that a black hole is a cosmic sensor, an information shredder that reduces everything it touches to bland simplicity. It states without apology that the unique story of what falls in is annihilated. On the other, the entire edifice of quantum mechanics, the most successful scientific theory in human history, screams that this is impossible. It declares that the erasure of information is forbidden a violation so profound it would cause the entire logical structure of the universe to collapse. It would mean that the past could be disconnected from the future. It would mean that reality itself could spring from nothing and dissolve into nothing. One of these two titanic theories, the foundations of all modern physics, must be wrong, or, at the very least, catastrophically incomplete. For a time, this paradox remained a philosophical puzzle, a debate for theorists to ponder over chalkboards. The information, after all, was still times, just locked inside the black hole beyond our reach. But then, in the 1970 seconds, a young physicist named Stephen Hawking decided to mix the oil and water of physics. He dared to apply the strange rules of quantum mechanics to the unforgiving edge of a black hole's event horizon. What he discovered would transform the paradox from a worrisome puzzle into a raging five-alarm fire at the heart of physics. Hawking found something that should not exist. He discovered that black holes are not completely black. Through a bizarre and ghostly quantum process occurring right at their edge, they leak. They radiate a faint, almost undetectable shimmer of particles into space, a thermal glow now known as Hawking radiation. This radiation carries energy away from the black hole, and because energy and mass are two sides of the same coin, as Einstein taught us, this means the black hole is slowly, painstakingly losing mass. It is evaporating. The process is astoundingly slow. For a black hole the mass of our Sun, it would take longer than the current age of the universe, trillions upon trillions of years, for it to disappear. But the conclusion is inescapable. Given enough time, every black hole in the universe will radiate itself away until there is absolutely nothing left. A slow cosmic sigh, and then it is gone. And with this revelation, the paradox ignites into a full-blown catastrophe, because now there is nowhere left for the information to hide. If the black hole, the ultimate prison, eventually vanishes completely, what happens to the library of information it was meant to be holding? Where did the story of the star it devoured go? What became of the cosmic blueprint for the worlds it consumed? The radiation Hawking described seemed to be purely thermal, a random hiss of energy. It was generic, carrying no intricate message from the interior. It was like getting a blast of random noise from the smoke of our burned book, with none of a computer's ability to decode it. It seemed to be informationless. So this is the chasm that has opened up before us, a crack in the very foundations of reality. If the information is sealed inside the black hole, it is lost forever when the black hole evaporates. This act of cosmic erasure would violate quantum mechanics. It would mean our most fundamental picture of the universe is wrong. But if the information somehow gets out, how does it escape? How does a message from within the ultimate prison get past a warden as implacable as the event horizon, a barrier that not even light can cross? To escape would violate the core principles of general relativity, the very theory that defines what a black hole is. It would break causality. It would mean an effect could precede its cause. We are left with a terrifying choice. Either Einstein is wrong, or the quantum pioneers were wrong. Either information can be destroyed, or it can escape from a place from which nothing is supposed to escape. This is the black hole information paradox. It is not merely an academic question. It is a profound mystery that forces us to confront the limits of our knowledge, to question the very nature of space-time and reality itself. Solving it is the single greatest challenge in theoretical physics today. For somewhere in the answer lies the next revolution, a deeper theory of the universe that can unite the warring kingdoms of the large and the small into a single cohesive whole. The search for that answer takes us on a journey to the wildest frontiers of human thought. We must travel to the strange quantum foaming edge of the event horizon. We must imagine the unimaginable chaos at the singularity, and we must dare to ask a question that seems like science fiction. What is information really, and is our universe a hologram? The battle to save the soul of physics has begun. What happens to a story when its book is thrown into an impossible fire? A fire so absolute that it consumes not just the paper and the ink, but the very ideas they represent, the very memory that a story ever existed. This isn't a philosopher's riddle. It is the single most profound question in modern physics. a question that threatens to shatter our understanding of reality itself. And to find its origins, we must journey back not to the far-flung future, but to a time when the universe was being reimagined. We must return to the dawn of the 20th century, to the mind of a single man who tore down a 200-year-old conception of the cosmos, replacing it with something far stranger and far more beautiful. For centuries, our universe was Isaac Newton's universe. It was a grand cosmic clockwork mechanism, predictable, orderly, and absolute. Space was a rigid, unchanging stage, a static grid upon which the celestial drama unfolded. Time was a universal metronome, ticking at the same rate for everyone, everywhere. And gravity. Gravity was a mysterious force, an invisible tether reaching across the void, instantly pulling objects toward one another. It worked, it was elegant, and for over 2 centuries it was enough. But then came Albert Einstein. He wasn't satisfied with a mysterious, instantaneous force. He felt that the universe should be more intimate, more interconnected. His thought experiments, born not in a laboratory but in the boundless theatre of his mind, led him to a revolutionary conclusion, a concept so profound it would forever alter our place amongst the stars. He proposed that space and time were not separate, rigid entities. They were woven together into a single dynamic, 4-dimensional continuum spacetime. This was no longer a passive stage, it was an active participant in the cosmic dance. Imagine it as a vast taut sheet of cosmic fabric. In this new vision, matter and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. A planet doesn't orbit the sun because of a mysterious, invisible rope. It follows the straightest possible path through a region of space that has been warped and distorted by the sun's immense mass. The sun creates a deep depression, a gravitational well in the fabric of space-time, and the Earth, like a marble rolling around the rim of a bowl, is simply following the curve. This was general relativity. It was a symphony of mathematics, a theory of sublime beauty that described the grand waltz of planets, stars, and galaxies with breathtaking precision. It predicted the gentle bending of starlight as it passed a massive object, a celestial lensing effect, later confirmed during a solar eclipse, catapulting Einstein to global fame. His equations were seen as a new gospel of the cosmos, a perfect description of the force that sculpts the universe. But buried deep within the heart of his elegant mathematics, a monster was lurking, a ghost in the machine. Einstein himself didn't see it at first. His theory was meant to describe the gentle curves of planets and the majestic sweep of galaxies. It was not meant to break, but the equations were uncompromising. They held a secret, a prediction so bizarre, so utterly alien, that Einstein himself refused to believe it could be real. The revelation came not from a pristine Swiss patent office or a quiet university study, but from the blood-soaked horror of the First World War. In 1915, a German physicist named Karl Schwarzschild was serving on the Russian front, calculating artillery trajectories amidst the deafening roar of cannons. Yet, in that chaos, he found the mental space to turn his attention to Einstein's newly published theory of gravity. While shells tore through the sky, Schwarzschild pursued an abstract cosmic problem. What would the curvature of space-time look like around a single, perfect, non-rotating sphere of mass? He sought a pure, simple solution, and what he found would haunt physics forever. Schwarzschild discovered that if you could compress enough mass into a small enough space, the curvature of space-time would become infinite. The gravitational well would cease to be a gentle depression. It would become a bottomless pit, a point of no return. Einstein was impressed by the mathematical rigor of Schwarzschild's solution, but he was appalled by its physical implications. He dismissed it as a mathematical curiosity, a flaw in the equations that nature would surely never allow. The universe, he argued, would have some mechanism to prevent such a complete and total gravitational collapse. Matter could not simply vanish from existence into a point of infinite density. It was too absurd, too grotesque. For decades, this dark star, as it was sometimes called, remained a fringe idea, a theoretical nightmare confined to the blackboards of physicists. But the universe, it turns out, is far more imaginative and far more violent than even Einstein could have foreseen. Astronomers began to understand the life cycles of stars, realizing that the most massive among them would not die peacefully. When a colossal star, many times the mass of our Sun, exhausts its nuclear fuel, the outward push of fusion that held it up for millions of years suddenly ceases. In that instant gravity, the relentless sculptor wins its final victory. The star's core collapses in upon itself in a fraction of a second, a cataclysm of unimaginable force. The outer layers are blasted away in a supernova, an explosion so bright it can outshine an entire galaxy. But the core, the stellar heart, keeps falling inward. If it is massive enough, there is no known force in the universe that can stop the collapse. No new state of matter, no quantum pressure, nothing. The star's remnant continues to shrink past the density of an atomic nucleus, past any conceivable physical state, crushing itself down, 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 until it tears a hole in the very fabric of reality. Schwarzschild's mathematical monster was real, and it had a name coined years later by the physicist John Wheeler, the black hole. To understand the true nature of this object is to confront the limits of our intuition. Let's embark on a journey, a final voyage into one of these cosmic enigmas. As your ship approaches, you see nothing. Not a dark sphere against the stars, but a perfect absence. It is a patch of sky from which no light emanates, a hole in the universe defined only by the halo of distorted starlight swirling around its perimeter. This boundary, this shimmering edge of darkness, is the most infamous border in all of creation. It is the event horizon. It is not a physical surface you could touch or land upon. There is no signpost, no warning bell. It is something far more profound, a one-way membrane woven from pure geometry, a waterfall in space-time so steep that once you tip over the edge, the direction down is the only direction left to travel. From a safe distance, your crewmates watch you drift closer. To them, something strange begins to happen to your perception of time. As you fall deeper into the black hole's gravitational well, the relentless ticking of your clock from their perspective appears to slow down. The light signals you send back to them become stretched, their wavelengths elongated, shifting from blue to green to red, a process known as gravitational redshift. Your messages become slower, your movements more languid. As you reach the event horizon itself, time for you, as seen by your friends, grinds to a complete and utter halt. They would see your image frozen for an eternity at the edge of oblivion, your final moment stretched out and painted onto the horizon, slowly fading as your light signal redshifts into nothingness. They will never ever see you cross, but for you the experience is tragically different. There is no pause, no grand moment of transition. You sail across the event horizon without so much as a bump. One moment you could have fired your rockets and escaped back into the familiar universe. The next moment you cannot. Escape is no longer a matter of engineering. It has become a logical impossibility. The very fabric of space-time inside the horizon is altered. Here, space and time swap their traditional roles in a bizarre cosmic inversion. The spatial dimension pointing toward the center of the whole becomes time-like. Moving towards the center is now as inevitable as moving towards next Tuesday. All possible futures, all paths you could possibly take now lead to one single, inescapable destination. The journey is swift and brutal. Tidal forces, the same gentle forces that raise the oceans on Earth, become monstrous here. The gravity at your feet, being infinitesimally closer to the center, is so much stronger than the gravity at your head that you are stretched. Your body, your ship, the very atoms you are made of are drawn out into a thin stream of incandescent plasma, a process grimly nicknamed spaghettification. You are unwritten, disassembled atom by atom, but even this utter destruction is not the end of the story. Your constituent particles, the fundamental bits of what was once you, continue their inexorable plunge. They are headed for the heart of the abyss. They are headed for the singularity. Here our language fails us. Our physics breaks down. The singularity is the ultimate unknown, the point where the story of space-time ends. According to general relativity, it is a point of zero volume and infinite density where all the mass of the collapsed star and everything that has ever fallen into the black hole is crushed out of existence. It is a place where the curvature of space-time becomes infinite, where the concepts of here and now lose all meaning. It is the graveyard of physics, a place where all the known laws of nature are ground into dust. And in this classical picture born from Einstein's theory, this is the final resting place of everything that crosses the event horizon. The star that died to create the whole. The asteroids and dust clouds it consumed over billions of years. The light from distant galaxies that strayed too close. And you, your unique arrangement of atoms, the complex electrical patterns in your brain that held your memories, your hopes, your consciousness, all of it, according to the theory, is funneled into this single, infinitely small point and utterly annihilated. The information that constituted you is erased from the cosmic ledger. Gone. Forever. This idea gave rise to one of the most elegant and terrifying concepts in astrophysics, encapsulated in a simple phrase, "A black hole has no hair." This was John Wheeler's way of saying that once a black hole forms, it becomes a remarkably simple object, a perfect cosmic amnesiac. It retains no memory of the complex, detailed things it was made from. Whether it was born from a star of hydrogen and helium, a swarm of asteroids made of iron, or a sophisticated information-rich starship, the end result is the same. The black hole settles into a state of perfect, featureless equilibrium, describable by only three numbers: its mass, its spin, and its electrical charge. All the other information, all the other properties, the hair is shaved away, lost forever, behind the impenetrable veil of the event horizon. The universe from the outside can no longer tell the difference. A black hole made from 1 billion tons of encyclopedias is utterly indistinguishable from a black hole of the same mass made from 1 billion tons of pure iron. The stories in those books, the intricate knowledge they contained, would in this classical view be gone. Not just scrambled, not just hidden, but fundamentally and irrevocably deleted from reality. This was the state of our understanding for half a century. Einstein's beautiful theory had given birth to the universe's most perfect prisons, celestial voids that were both inescapable and forgetful. They were the ultimate cosmic dead ends, places where the rich tapestry of the universe was unraveled and its threads discarded. For a time, this was not seen as a problem. It was just another bizarre yet self-consistent feature of our strange cosmos. The information was lost, but it was lost in a place we could never access anyway, so perhaps it didn't matter. But a revolution was coming. A different way of looking at the universe, born from the strange and probabilistic world of the atom, was about to collide head-on with Einstein's grand, deterministic vision of gravity. Quantum mechanics, the physics of the very small, had its own set of sacred, unbreakable laws. And its most fundamental principle, its central commandment, was that information can never ever be truly destroyed. The universe, according to quantum physics, must be a perfect historian. It must always remember what it was made of. So what happens when the universe's most perfect information shredder meets a law of physics that says information is eternal? What happens when the quantum world arrives at the edge of a black hole? The two great pillars of 20th century physics, general relativity and quantum mechanics, were on a collision course. One of them, or perhaps both, would have to break. The paradox was set, the lines were drawn, and a scientific battle for the soul of reality was about to begin. For a century, our portrait of a black hole was one of absolute finality, an object carved from the ink of pure nothingness. We had come to accept them as the universe's perfect prisons, cosmic oubliettes from which nothing, not even a whisper of light, could ever return. Einstein's equations, elegant and unyielding, described a one-way journey into oblivion, a place where space-time itself collapsed into an unknowable point of infinite density. This was the accepted truth, a cornerstone of cosmology, the period at the end of a cosmic sentence. The black hole was a passive entity, a silent gravitational trap waiting patiently for the unwary. It consumed, it grew, and it endured for eternity, a permanent scar on the fabric of reality. The laws of the universe, we thought, stopped dead at its edge, surrendering to its perfect and perpetual darkness. But the universe rarely conforms to our sense of poetic finality. While general relativity painted its grand, sweeping portrait of gravity and space-time, another revolution had been raging on a different scale. This was the world of quantum mechanics, the bizarre and probabilistic kingdom of the very small. Here, certainty dissolved into a haze of possibilities, and solid matter flickered in and out of existence. For decades, these two great pillars of 20th century physics stood apart, magnificent in their own domains, but stubbornly incompatible. Gravity ruled the stars and galaxies, the grand cosmic dance. Quantum mechanics governed the atom and its constituents, the frenetic unseen world beneath. They were two languages describing the same reality, yet they could not speak to one another. Nowhere was this schism more apparent, more violently irreconcilable than at the event horizon of a black hole, a place where immense gravity and infinitesimal scales were forced into a cataclysmic confrontation. It would take a mind of singular brilliance and unimaginable courage to venture into that theoretical no man's land and listen for what it had to say. That mind belonged to a young physicist at Cambridge University, Stephen Hawking. In the early 1972, he was not seeking to rewrite the cosmos. His initial calculations were an attempt to apply the strange rules of quantum mechanics to the well-behaved spacetimes just outside time's a black hole's boundary. He wanted to understand how the intense gravitational curvature of the event horizon might affect the particles that roamed nearby. It was a rigorous mathematical exercise, an attempt to stitch together the frayed edges of our two greatest theories. No one, least of all Hawking himself, expected the calculation to yield anything more than a subtle refinement of our existing models. No one expected it to reveal that the universe's perfect prisons were in fact leaking. The secret lay buried in one of the most unsettling concepts in all of physics, the nature of empty space. To our senses, a vacuum is the embodiment of nothingness, devoid of matter, energy, and activity. But quantum mechanics offers a profoundly different and deeply chaotic vision. On the microscopic level, the vacuum is not empty at all. It is a seething, roiling foam of furious activity, a tempest of phantom energy. Out of this abyss, particles are constantly erupting into existence, borrowing a sliver of energy from the universe itself. These are virtual particles appearing in matter-antimatter pairs, a positron and an electron, a quark and an antiquark. They exist on a cosmic loan, an energy debt that must be repaid almost instantly. They flash into being for an immeasurably small fraction of a second before colliding with their antimatter twin and annihilating one another, vanishing back into the nothingness from which they came, their brief existence perfectly balanced, their debt settled. All of this happens on timescales so fantastically short and distances so impossibly small that the universe on average still appears empty and calm. It is a hidden, ghostly dance that underpins the very fabric of our reality. Hawking's profound insight was to ask what happens to this quantum foam at the most extreme edge in the universe, the event horizon of a black hole. Imagine one of these virtual particle pairs popping into existence right on that precipice, that point of no return. In the quiet of deep space, they would simply annihilate and disappear, their fleeting lives unnoticed. But here, the gravitational gradient is so severe, so brutally steep, that space is being pulled into the black hole faster than the speed of light. Now a strange and fateful possibility arises. One of the virtual particles, say the antiparticle, might be born just inside the horizon, while its twin materializes just outside. Before they have a chance to annihilate, the chasm of the event horizon separates them forever. The one inside is immediately dragged into the singularity, its fate sealed. It can never escape to repay its energy debt. But the other particle, stranded just outside the boundary, is now an orphan. It cannot follow its partner, nor can it simply vanish, as that would violate the fundamental law of conservation of energy. To settle the cosmic books, the universe improvises a desperate solution. The particle that fell into the black hole is assigned a negative energy. By consuming this negative energy, the black hole pays the universe back for the creation of the pair. And in physics, losing negative energy is exactly the same as losing mass. A tiny, almost imperceptible fraction of the black hole's own mass energy is sacrificed to promote the orphaned virtual particle outside into a very real, tangible particle. It is no longer a phantom, it is now a particle of light or matter, a real entity free to escape into the wider universe. To a distant observer, this escaping particle would appear as if it had been spat out, emitted directly from the black hole itself. The perfect prison had sprung a leak. This phenomenon, which would come to be known as Hawking radiation, was a lightning strike that illuminated the entire landscape of physics. It meant that black holes were not truly black, they glow. not with the brilliant fire of a star, but with a faint, impossibly subtle thermal radiation, a cosmic ember slowly cooling in the void. For a black hole the mass of our sun, this glow is so fantastically weak that its temperature is only a fraction of a degree above absolute zero. Its energy output is vastly less than the energy it absorbs from the cosmic microwave background radiation left over from the Big Bang. Such a black hole is for now still growing, not shrinking. But this is only a temporary reprieve. As the universe continues to expand and cool, the background radiation will fade. Eventually, even the faintest heat from the black hole's glow will be greater than the energy it takes in, and then the process of evaporation will begin in earnest. This evaporation is a process of breathtakingly patient self-destruction. A solar mass black hole would take an estimated 10 to the power of 67 years to evaporate completely, a number so colossally large that the current age of the universe is a fleeting instant by comparison. A supermassive black hole at the center of a galaxy might take 10 to the power of 100 years, a googol of years, to radiate away its substance. They are not eternal, but their lifespans make the stars themselves seem like ephemeral sparks. Yet the principle was unshakable, a direct consequence of combining our two best theories of reality. Black holes have a finite life. They are born in the cataclysm of stellar collapse. They live and feed for eons, and then particle by painstaking particle they shrink, they wither, and eventually, after a final flash of high-energy gamma rays, they disappear from the universe entirely. This was a revolutionary discovery, a Nobel-worthy insight that completely redrew our map of the cosmos. It transformed black holes from static, passive objects of general relativity into dynamic, thermodynamic entities that participated in the life of the universe. They had a temperature, they had an entropy, they followed laws previously reserved for steam engines and refrigerators. It was a triumph, a stunning testament to the power of theoretical physics to reveal the universe's deepest secrets. But as the implications of Hawking's discovery settled in, a sense of profound unease began to creep through the physics community, because within this beautiful new theory a monster was lurking, a paradox so deep, so fundamental, that it threatened to bring the entire edifice of modern physics crashing down. The problem wasn't that black holes died, the problem was how they died. To understand the crisis, we must first grasp one of the most sacred, non-negotiable principles in all of science, the conservation of information. This isn't about information in the everyday sense, like the words on a page or the data in a computer. In physics, information refers to the complete, unique quantum description of a particle or a system of particles. It is the precise specification of every property, position, momentum, spin, charge that makes an object what it is. It is the universe's perfect, incorruptible ledger. Quantum mechanics is built upon a central axiom known as unitarity, which declares that this information can never ever be truly destroyed. It can be scrambled, rearranged, or hidden, but it must always be preserved. If you burn a book, you might think the information within it is gone forever. But a physicist would tell you that in principle, if you could capture every single particle of smoke and ash, every photon of heat and light, and precisely measure their quantum states, you could reconstruct the original book perfectly. The information isn't destroyed, it's just dispersed in an incredibly complex and impractical way. This principle is the bedrock of causality. It ensures that if we know the complete state of the universe at one moment, we can, in theory, calculate its exact state at any point in the future or the past. Without unitarity, the deterministic chain of cause and effect is broken. The universe becomes fundamentally unpredictable, a magical realm where things can simply pop into or out of existence for no reason. And this is where Hawking's discovery ignited a firestorm. His calculations showed that the radiation escaping from a black hole is perfectly thermal. This is a critical and devastating detail. Thermal radiation is by its very nature random and generic. It is a featureless hiss of energy like the static on an old television. Its properties depend only on the black hole's mass, charge and spin, not on the unique specific things that fell into it. Imagine you have two black holes of identical mass. Into one you throw a star made of hydrogen and helium. Into the other, you throw an equivalent mass of encyclopedias containing all the collected knowledge of humanity. According to Hawking's equations, as these two black holes evaporate over the next Google years, the radiation they emit will be absolutely perfectly identical. The escaping particles carry no trace, no echo, no ghost of the intricate structures that created them. The complex quantum information of the star's plasma and the encyclopedia's atoms has been completely laundered, replaced by a generic characterless glow. Now follow this to its terrifying conclusion. We wait for eons upon eons until the black hole has radiated away its very last particle and vanished completely. Nothing is left. There is no singularity, no event horizon, just empty space filled with this uniform thermal radiation. So where did the information go? Where is the quantum ledger that described the star or the encyclopedias? The radiation itself contains none of it. The black hole is gone, so it cannot be hiding inside. It seems to have been utterly and completely erased from existence, wiped clean from the cosmic hard drive. This was the bombshell. A black hole in its life and death appeared to be a machine for destroying information. Here, the two pillars of physics were no longer simply failing to speak to each other. They were screaming at each other across an unbridgeable chasm. General relativity, with its prediction of a singularity, a point of infinite density where the laws of physics break down, was perfectly comfortable with the idea that information could be crushed out of existence. It provided a place, a mechanism for the universe to forget. But quantum mechanics recoiled in horror. Its most fundamental law, the principle of unitarity, was being violated. If Hawking was right, then the quantum world was not a predictable deterministic system. It was a lie. The connection between past and future was severed. The ability to understand the universe through the unbroken chain of cause and effect would be lost. Physics, as we knew it, would cease to function. This was the black hole information paradox. It was not a minor quibble or a mathematical loose end. It was a declaration of war between the two most successful theories in human history, fought on the battlefield of a black hole's dying breath. The universe cannot have two sets of rules. It cannot be both perfectly predictable and fundamentally random. One theory had to be wrong, or at the very least, woefully incomplete. Was Stephen Hawking's calculation the final word, a death sentence for the quantum dream of a knowable universe? Or was there a subtle flaw in his reasoning, a hidden loophole that could rescue reality from this plunge into absurdity? Lines were drawn. Physicists around the world were forced to choose a side. For the next 2 decades, a titanic intellectual struggle would ensue, a conflict that would push the human imagination to its absolute limits, forcing us to question the very nature of space-time and reality itself. The quiet, eternal prison had found its voice, and it spoke of a deep and terrible contradiction at the very heart of the cosmos. And so the calculation was on the table, a mathematical testament as elegant as it was terrifying. Stephen Hawking's discovery was not some esoteric footnote in the grand cosmic story. It was a declaration of war. A quiet, unassuming thermal hiss emanating from the edge of oblivion had just placed a siege engine at the gates of quantum mechanics, threatening to tear down the most successful theory in the history of science. For a time, the physics community existed in a state of suspended disbelief. The implications were so profound, so utterly heretical, that the initial reaction was to search for a flaw, a simple misstep in the logic. Surely there had to be an error in the derivation. Perhaps the semi-classical approximation used to merge the worlds of the very large and the very small was too crude. Perhaps some subtle quantum effect unaccounted for would emerge to rescue the information from its fiery tomb. Physicists scoured the equations, ran the thought experiments again and again, hoping to find a loose thread, a mathematical loophole that would allow the universe's most fundamental law to remain intact. But the thread wouldn't fray. The logic held firm, its conclusion as inescapable as the gravity of the black hole itself. The radiation was thermal. For it to be truly perfectly thermal, it had to be random, a featureless glow with no memory of the intricate complex objects that had collapsed to form its parent black hole. A star, a planet, an encyclopedia, your own hand, each one is a unique tapestry of quantum information. Dropped into a black hole, that tapestry would contribute to its mass. But as the black hole evaporated, the outgoing heat carried no pattern, no echo, no ghost of the story that had been fed to it. The information, it seemed, was gone, not just scrambled or hidden. It was annihilated, erased from the cosmic ledger forever. This was the moment the ground began to shift beneath their feet. The gentle tremor of a curious academic problem was rapidly escalating into a seismic event, a full-blown crisis that threatened to split the world of physics in two. The paradox was no longer a puzzle. It was a monster, and it was staring directly into the heart of everything we thought we knew. Faced with this abyss, the community fractured, forced to contemplate the unthinkable. The first path, the most direct and brutal, was to simply accept Hawking's result at face value. This was the ultimate heresy. It meant declaring that information can, in fact, be permanently destroyed. To a non-physicist, this might sound like a minor philosophical point, a rule that can be bent. But to a physicist, it is blasphemy. Quantum mechanics is built upon an unbreakable commandment, unitarity. This principle guarantees that if you know the complete quantum state of a system at any one time, you can in principle calculate its exact state at any point in the past or future. It is the universe's promise of cause and effect. It is the reason the cosmos is not a chaotic, unpredictable fever dream. Unitarity means that information is never truly lost. You can burn a book, but the information it contained is merely transformed. It is encoded in the chemical composition of the ash, the precise trajectories of the smoke particles, the specific frequencies of light and heat radiated away. An all-powerful observer could in theory reverse the process, collecting every single particle and photon to reconstruct the original text. The story, though, scattered to the winds, still exists, but the black hole was proposing something far more sinister. It wasn't just burning the book, it was erasing the very concept of the letters themselves. It was a one-way street to nothingness, a place where the universe's memory failed. If information could be destroyed here, in this one exotic location, then the principle of unitarity wasn't a fundamental law at all. It was just a suggestion, a local bylaw that could be violated. And if it could be violated once, the entire edifice of quantum theory would begin to crumble. The predictability it promised would become an illusion. The elegant evolution of quantum states through time, described by the Schrödinger equation, would be fundamentally wrong. It would mean that deep within the quantum realm, a hidden randomness lurks, an intrinsic uncertainty that goes far beyond the famous fuzziness of Heisenberg. A black hole wouldn't just be a gravitational anomaly. It would be a hole in the very logic of existence, a place where the universe could forget itself. For many, this was a price too high to pay. To abandon unitarity was to abandon the foundational belief that the universe is at its core rational and knowable. It felt like giving up, like admitting that magic was real. It was an intellectual surrender of the highest order. This profound reluctance to sacrifice quantum mechanics drove physicists down a second, equally desperate path. If information cannot be destroyed, then it must times escape. The conclusion was inescapable. But how Hawking's calculation was robust, the radiation trickling out during the black hole's long life was stubbornly thermal. This left only one seemingly absurd possibility: the information doesn't come out gradually. Instead, it remains locked inside, becoming ever more compressed as the black hole shrinks until the very last moment. In this scenario, the black hole doesn't evaporate into absolute nothingness. It evaporates down to a tiny subatomic nugget, a stable remnant of spacetime, no larger than a Planck length, the fundamental pixel of reality itself. And within this infinitesimal speck, all the information of everything that ever fell in would be perfectly preserved. Think of it, the quantum states of entire galaxies, the history of collapsed stars, the unique arrangements of atoms in countless worlds, all compressed and stored inside an object smaller than a single proton. This was the great hope. The information wasn't lost, it was just archived in a cosmic flash drive of unimaginable density. At first glance, this idea of a black hole remnant seemed like an elegant solution. It saved quantum mechanics from the chopping block and provided a neat, tidy repository for all that missing information. But as theorists began to poke and prod at the concept, it revealed itself to be a Pandora's box of its own intractable problems. The first and most glaring issue was one of storage capacity. The The Bekenstein bound, a deep principle of thermodynamics and gravity, states that the amount of information a region of space can hold is proportional to its surface area, not its volume. A black hole remnant being unimaginably small would have a minuscule surface area, yet it would need to contain a potentially limitless amount of information. A small solar mass black hole could swallow a planet containing vast stores of data. A supermassive black hole could devour billions of stars over cosmic eons. According to the remnant hypothesis, both would shrink down to the same tiny Planck-sized object. How could an object of a fixed, minuscule size hold a variable, potentially infinite library of cosmic history? It violated the fundamental thermodynamic rules that govern information itself. It was like trying to store the entire internet on a single grain of sand. The second problem was one of dynamics. How would this information ever get out? If the remnant is stable, the information remains locked away forever, which is functionally no different from it being destroyed. So for the information to be considered retrieved, the remnant must eventually decay. Imagine the final moment of evaporation. The black hole is now a microscopic dot, yet it holds the information of a star. In its final puff of existence, it must release that entire complex story. This couldn't be a gentle thermal whisper. To encode that much information into a small burst of particles would require a violent explosive release of immense energy, a final information-rich scream from the singularity. Yet this directly contradicted Hawking's original calculation, which showed the process remaining gentle and thermal all the way to the end. The remnant theory required a dramatic final act that the physics of evaporation simply did not support. There was no known mechanism that could orchestrate such a carefully choreographed data dump at the very end of spacetime. And then came the final, perhaps most devastating blow from the world of cosmology. If black hole remnants were the solution, the universe should be teeming with them. Any star above a certain mass can collapse into a black hole. In the early violent universe, conditions were ripe for the creation of countless primordial black holes. If every single one of these objects, large and small, left behind a stable Planck-scale particle after evaporating, where are they all? These remnants would be a form of matter interacting with the cosmos only through their immense gravity. They would be, in effect, a new type of dark matter. But when cosmologists ran the numbers, the theory produced a catastrophic result. The predicted density of these remnants was enormous, far greater than any allowable limit on the amount of matter in the universe. Their collective gravitational pull would have drastically altered the expansion of the cosmos, distorting the cosmic microwave background and warping the formation of galaxies in ways we simply do not observe. The sky is not full of these cosmic data nuggets. Their predicted existence was a flagrant contradiction of the universe we actually see. The cure, it turned out, was perhaps worse than the disease. So here it was, the Great Schism. The scientific community stood at a fork in the road with both paths leading off a cliff. On one side stood the defenders of general relativity and Hawking's seemingly flawless calculation. They were forced to accept the death of information, a conclusion that meant our cherished quantum rulebook was at best a beautifully detailed approximation of a deeper, non-unitary reality. It meant accepting a fundamental level of unknowability, a point past which the laws of cause and effect simply dissolved into a gravitational mist. On the other side stood the guardians of quantum mechanics, defending the sanctity of information at all costs. They were forced to postulate the existence of bizarre, physically problematic remnants, infinitely dense databanks that violated thermodynamics, required unknown explosive physics, and should have saturated the universe, yet were nowhere to be seen. Each camp was defending a pillar of modern physics, but only by proposing a radical, unproven, and deeply unsatisfying alteration to our understanding of the cosmos. There was no easy middle ground, no simple compromise. This was the break in its starkest form. For nearly a century, general relativity and quantum mechanics had coexisted peacefully, each reigning supreme in its own domain, the cosmic and the subatomic. They were the two great symphonies of 20th century science, and while we knew they were written in different keys, we always assumed they could one day be played in harmony. The black hole information paradox was the first time they were forced to play the same note, and the result was a horrifying, deafening dissonance. It was the sound of our two most fundamental descriptions of reality screaming at each other. It was the irrefutable mathematical proof that our picture of the universe was not just incomplete, but profoundly, fundamentally broken at its core. One of our gods had to fall. Either Einstein's elegant geometric vision of space-time needed a radical overhaul, or the quantum laws that govern all of matter and energy were built on a foundation of sand. This moment of crisis, this intellectual deadlock, was not an ending. It was a violent, necessary beginning. The paradox had closed all the familiar doors, locked all the conventional exits. It forced physicists to abandon the comfortable assumptions they had held for decades and to start thinking in ways that were once considered the realm of science fiction. The sheer intractability of the problem was a signal that we were missing something enormous, a piece of the cosmic puzzle so essential that without it our theories were producing nonsense. We weren't just looking for a new particle or a new force. We were looking for a new principle of reality, something as profound as relativity or quantum theory itself. The contradictions were so sharp, the stakes so high, that any potential solution, no matter how wild, had to be considered. The break had occurred, the chasm had opened, and now the challenge was to build a bridge. But what strange new architecture, what unheard of materials could possibly span the gap between the smooth, unbroken world of Einstein and the chaotic, quantized world of the atom? The crisis demanded a revolution, and the search for that revolution would take us to the very edge of reality, to a place where space-time itself might be nothing more than an illusion. And so the beautiful, delicate compromise shattered. For decades, a belief in something called complementarity had provided a kind of conceptual balm, a gentleman's agreement, suggesting that an observer could never witness both sides of the paradox at once, thus allowing reality to maintain a fragile, state-dependent consistency. It was an elegant solution, a way to keep the peace between the warring titans of general relativity and quantum mechanics. But as we saw, the sharpest minds in physics began to pick at its threads, running thought experiments of ever-increasing complexity until the entire tapestry unraveled. The peace was over. The ceasefire had failed. What followed was not a neat and tidy progression toward truth, but a descent into chaos. Physics had lost its map in the darkest part of the forest, and every direction seemed to lead over a cliff. This was the new Wild West of theoretical inquiry, a frontier where the old laws were suspended and every assumption was now subject to challenge. The community found itself in a state of profound intellectual crisis because the paradox was no longer a distant academic curiosity. It had become a gaping wound at the very heart of our understanding of the universe, and it was bleeding. The search for a resolution became more frantic, more desperate. Physicists were no longer just trying to patch a hole. They were trying to save the entire ship from sinking. They were forced to consider ideas that were once relegated to the fringe concepts so radical they made black holes themselves seem mundane. If our most trusted principles were leading us to a logical contradiction, then one of them had to be wrong. But which one would we sacrifice? The sanctity of quantum information, which underpins all of modern physics, or the smooth, serene geometry of space-time, Einstein's greatest masterpiece? It was an impossible choice, a devil's bargain. For a time it seemed that no one could find a way forward. The problem was too hard, the implications too terrifying. And then in 2012, four physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, decided to press on the wound hard. They didn't try to soothe the paradox. They sharpened it. They took the established logic to its absolute agonizing breaking point, and in doing so unleashed an idea so violent and so heretical that it threatened to burn down everything we thought we knew about a black hole's edge. They proposed a monster. They proposed a wall of fire. To understand the sheer terror this idea induced, you have to follow their logic, a chain of reasoning as impeccable as it is horrifying. Let's return to our entangled particles born from the quantum foam at the event horizon. One partner, let's call her Annie, falls into the black hole destined for the singularity. Her twin Ben escapes into the cosmos as a particle of Hawking radiation. As we've established, their fates are quantumly intertwined. They are two sides of the same coin forever connected by a vow of entanglement. Annie's information is locked inside the black hole while Ben's information is now part of the outgoing radiation. Now imagine you are an observer bob floating at a safe distance. You patiently wait for an almost unimaginable stretch of time. You watch as the black hole slowly, painstakingly evaporates, shrinking as it radiates away its mass particle by particle. You collect all the bends that fly out every single quantum of Hawking radiation that has ever escaped. Let's call this collected radiation System B. You wait until the black hole has passed its halfway point, the moment it has radiated away more than half of its initial mass and information. According to the foundational principles of quantum mechanics, the information that fell in must be coming back out. Therefore, the early radiation that you've already collected must be deeply entangled with the radiation that is times now, times emerging. The information is being reassembled bit by quantum bit. This is where the trap snaps shut. Let's consider a new particle of Hawking radiation, Chris, that has just been emitted from this now ancient shrunken black hole. For information to be conserved, for the universe's bookkeeping to be correct, Chris times must times be entangled with the radiation that came out earlier with your vast collection System B. This is the only way for the black hole's final state to be pure, to be a coherent quantum system, rather than a scrambled mess of random noise. It's the requirement of unitarity, the non-negotiable law, that quantum information cannot be destroyed. So Chris, the late particle, is entangled with Ben, the early particle. But wait, Chris also has an infalling twin, a partner we can call Chloe, who has just slipped across the event horizon. According to the same logic that created our first pair, Chris and Chloe must also times be entangled. They were born together at the horizon. Their connection is fundamental. And here, in this simple setup, AMPS exposed a fatal contradiction. The particle, Chris, flying out into space, is now required to be fully entangled with two separate systems simultaneously. It must be entangled with the early radiation Ben to save the law of information conservation, and it must also be entangled with its infalling partner Chloe to satisfy our understanding of how particles are created at the event horizon. Quantum mechanics has an ironclad rule for this situation. It is a principle as fundamental as any other, known as the monogamy of entanglement. It states quite simply that a quantum system cannot be fully entangled with two independent things at the same time. It's a vow of fidelity written into the fabric of reality. A particle can have a partial connection to many others, but it can only give its entire quantum soul its maximum entanglement to one partner. The outgoing particle, Chris, is being asked to be a bigamist in a universe that only allows monogamy. The logic leads to an impossible trilemma, a three-way paradox from which there is no peaceful escape. At least one of our most cherished beliefs about the universe, times must be wrong asterisk. Let's lay them out. First, there is the principle of unitarity, the idea that information is conserved. If we give this up, the paradox vanishes, but so does most of quantum mechanics. Second, there is the validity of our standard theory of quantum fields operating in curved spacetime, which predicts the entanglement between particles just inside and just outside the horizon. This is the very framework that gives us Hawking radiation in the first place. Third, and perhaps most sacred of all, there is Einstein's equivalence principle. This is the beautiful foundational idea that the laws of physics are the same everywhere, and that for a freely falling observer, gravity vanishes. It's the principle that guarantees your smooth, uneventful passage across an event horizon. No drama, no signs, no indication you have crossed the point of no return. The four physicists of AMPS looked at this impossible choice and made their move. They argued that the first two principles were too fundamental to abandon. Giving up on information conservation would effectively break physics, and the theory that predicts particle creation at the horizon seems robust. So, with what must have been a heavy heart, they jettisoned the third. They sacrificed Einstein's no-drama principle. They concluded that if the particle Chris cannot be simultaneously entangled with both its interior partner Chloe and the exterior radiation Ben, then the universe must make a violent choice. To preserve the older, more critical entanglement with the outgoing radiation, the universe must forcibly, cataclysmically sever the bond between Chris and Chloe at the very moment of their creation. But how do you break a quantum vow? Not with words. You break it with energy. An immense, shocking, overwhelming amount of energy. The calculations showed that the energy required to shatter this entanglement would manifest as a shell of super high energy quanta, a blistering membrane of particles heated to an impossible temperature encasing the event horizon. It wouldn't be empty space. It would be a wall of fire, a quantum firewall. The implications were breathtakingly radical. In this new terrifying vision, the event horizon is no longer a gentle, invisible boundary. It is the most violent place in the cosmos. For an astronaut falling toward the black hole, the end would not come at the singularity in a distant future. It would come instantly at the horizon itself. The moment you touched that threshold, you wouldn't slip through. You would be met by a thermodynamic executioner. You, your spaceship, every atom in your body would be vaporized, incinerated in a blast of pure energy. Your constituent information scrambled and immediately available to be radiated back out. There is no interior to the black hole in the way we imagined it. There is only a gateway to annihilation. This proposal solved the information paradox, but in the most brutal way imaginable. Information is never lost because it never truly gets locked inside. It's as if every book thrown into a library is instantly burned at the door, its smoky ashes then used to reprint the original text outside. The content is preserved, but the library is a lie. The interior of the black hole, that mysterious realm described by general relativity, is rendered inaccessible, perhaps even non-existent. The firewall paper, as it came to be known, landed like a thunderclap in the world of physics. It was not celebrated as a breakthrough. It was received with a mixture of horror, disbelief, and grudging respect. The logic was powerful, the conclusion almost inescapable, yet the result felt deeply, profoundly wrong. It felt like a violation of the aesthetic elegance that had guided physics for a century. Einstein's theory of general relativity is built upon the idea of smoothness of gentle, continuous curves in spacetime. The firewall introduced a jagged, violent quantum seam at its most delicate point. It was a graffiti tag on a masterpiece. Physicists around the world were aghast. Stephen Hawking himself, whose entire calculation started this journey, initially rejected the idea outright, finding it abhorrent. Others scrambled to find a flaw in the AMP's argument, a loophole, a way out of their seemingly airtight logic. The community was fractured. Some physicists began to defend the firewall, arguing that while it was ugly, it was the least ugly of the three impossible options. It was the bitter medicine that physics had to swallow to cure the disease of information loss. They argued that Einstein's equivalence principle was a classical idea, and it was always destined to break down at the quantum scale. The event horizon, they claimed, was exactly where this breakdown should occur. But for many more, the firewall was a monster that had to be slain. It felt like a step backward, a brute force solution that lacked the subtlety and depth the problem deserved. Breaking the gentle peace of the event horizon seemed too high a price to pay. It meant that a fundamental symmetry of nature, the very principle that ensures falling feels like floating, was not fundamental at all. It would mean that a freely falling observer could in fact tell they were at a special place in the universe. They would know it because they would be on fire. This violated the spirit, if not the letter, of relativity. The debate raged in conference halls, on university blackboards, and across countless scientific papers. It became the defining intellectual battle of its time. The chasm created by Hawking's paradox had now deepened into a seemingly impassable canyon. On one side stood the defenders of quantum purity, armed with the terrifying logic of the firewall. On the other side stood the defenders of Einstein's beautiful geometry, who insisted that spacetime could not have such an ugly, violent scar. And in between, a growing number of theorists started to explore even stranger possibilities, ideas that were once considered pure science fiction. Perhaps the very nature of space and time itself was the culprit. Perhaps the smooth continuum of the interior and the quantum reality of the exterior were connected in a way no one had ever imagined, through hidden bridges, through cosmic wormholes. The firewall had presented physics with an ultimatum: either accept this fiery end to Einstein's dream, or find an entirely new way of thinking about reality. The downward path had led us to the edge of a precipice. The old world was broken, and ahead lay only uncharted and perhaps uninhabitable territory. The search was no longer just for a solution, it was for a new map of the cosmos altogether, and so we were left at a profound and terrifying impasse. For decades, the greatest minds in physics circled this gravitational tomb, this perfect prison of space-time, and found only contradiction. On one side stood Einstein's majestic general relativity describing a smooth, curved universe, where the singularity was an absolute end, a point of no return, where information and matter were crushed into nothingness. On the other stood the unyielding laws of quantum mechanics, a world of fizzing, unpredictable certainty which declared with absolute conviction that information can never ever be truly destroyed. The paradox was not a mere academic puzzle. It was a schism running through the heart of reality itself. A black hole seemed to be the one place in the cosmos where the universe's two great rulebooks gave opposing commands, a place where one of them had to break. It felt like an unwinnable war fought in the silent darkness at the edge of existence. The battle had raged, theories had been shattered, and a generation of physicists had been humbled by this seemingly simple question. When you throw something into a black hole, where does it go? To save the soul of physics, the answer could no longer be nowhere. Something had to give. But what if the flaw wasn't in the physics, but in the question itself? What if we were looking for the lost information in the wrong place, or even in the wrong dimension? The solution, when it began to crystallize, did not come from a minor adjustment or a clever mathematical trick. It came from a conceptual detonation so powerful it threatened to vaporize our most fundamental assumptions about the nature of space reality and our own existence. It required us to see the universe not as a three-dimensional stage upon which events unfold, but as something far stranger, far more ethereal, a hologram. To understand this monumental leap, you must first forget the black hole as a volumetric object, as a three-dimensional sphere of darkness. Instead, you must see it as its boundary. Picture a perfect shimmering sphere suspended in the void, the event horizon. We've always seen it as a one-way door, a precipice. But a handful of brilliant theorists, beginning with Gerard, Hooft and Leonard Susskind, began to ask a radical question. What if the event horizon isn't just a boundary? What if it's a canvas? What if it's a vast cosmic storage medium, a two-dimensional surface with the capacity to hold a record of everything that has ever crossed it? This is the holographic principle, and it is as elegant as it is mind-bending. The idea proposes that all the information about the three-dimensional interior of the black hole, every particle, every quantum state, every last bit of data that has ever fallen in, is not lost to the singularity at all. Instead, it is intricately and completely encoded onto the two-dimensional surface area of its event horizon. Think of a common hologram, the kind you might find on a credit card. It's a flat, two-dimensional piece of plastic film. Yet when light strikes it in just the right way, it projects a fully realized three-dimensional image. The entire description of that 3D object, its depth, its texture, its form, is contained within the pattern etched onto the 2D surface. Now scale that idea up to the scale of the cosmos. The holographic principle suggests that the black hole's event horizon is that film. The chaotic, unknowable three-dimensional interior, including the dreaded singularity, might be nothing more than a grand projection, a ghostly image generated by a more fundamental two-dimensional reality living on its surface. This wasn't just a wild guess. It was rooted in a startling mathematical discovery made years earlier by Jacob Bekenstein. He had been pondering the entropy of a black hole, a measure of its information content, its internal disorder. In our everyday world, entropy scales with volume. A larger room can hold more disordered things than a smaller one, so everyone expected that a black hole's information capacity would depend on its three-dimensional volume. Bekenstein, however, found something utterly bizarre and counterintuitive. He calculated that the entropy of a black hole, its total information content, was directly proportional not to its volume, but to the surface area of its event horizon. This was a result so strange that many, including Stephen Hawking at first, refused to believe it. It was like discovering that the amount of data you can store on a hard drive depends not on the number of magnetic platters inside it, but only on the surface area of its outer casing. It made no logical sense in a 3D world, but within the framework of the holographic principle, it is the crucial central clue. It is the universe screaming at us that we are thinking about space in the wrong way. The information isn't times in times the volume, The information times is times the surface, and the volume is just its shadow. The true cosmic ledger, the ultimate record book, isn't the 3D space we perceive, but the 2D boundary that contains it. Every particle that plunges past the event horizon leaves an imprint, a unique signature woven into the very fabric of that boundary. Imagine the event horizon as a screen of unimaginable resolution, a canvas made of the smallest possible units of area known as Planck areas. Each of these pixels, quadrillions of times smaller than a proton, can hold a single binary bit of information, a yes or no, a 1 or a 0. As a star collapses, or an astronaut falls in, their constituent particles don't just vanish. Instead, their quantum information is translated and meticulously tattooed onto these Planck-scale pixels on the horizon's surface. The black hole's surface grows as it consumes matter, creating more Planck areas, more cosmic memory to store the information of its victims. The event horizon is no longer a simple membrane. It becomes a shimmering, complex tapestry of encoded data, a two-dimensional chronicle of everything it has ever swallowed. But this profound realization that the information is preserved on the surface only solves half the puzzle. If the data is safely written onto this cosmic hard drive, how is it ever read? How does it escape back into the universe to uphold the laws of quantum mechanics? This is where Stephen Hawking's own momentous discovery, the very mechanism, started. The paradox comes back to provide the astonishing solution. Hawking radiation, once thought to be the agent of information destruction, is now reimagined as the universe's most patient and subtle data retrieval system. We previously understood this radiation as arising from pairs of virtual particles popping into existence at the event horizon, with one falling in and the other escaping. In our earlier, simpler model, the escaping particle was random thermal and carried no useful information. It was pure heat, the featureless ash of a cosmic fire. But the holographic principle completely reframes this process. The radiation is not random at all, it is the playback. As those virtual particles are wrenched apart at the horizon, the escaping particle is not created in a vacuum of ignorance. It is intricately quantum mechanically entangled with the very Planck-scale pixels of the horizon from which it springs. It interacts with the encoded information on that 2D surface. The escaping particle is subtly altered by the data it touches. It carries away a single, infinitesimally small, hopelessly scrambled piece of the original information that fell in long ago. One particle might carry a faint echo of the spin of an electron from a doomed star. Another might hold a whisper of the momentum of a hydrogen atom that fell in a billion years later. It's not a clear message. It's a symphony of scrambled data broadcast, one quantum note at a time over unimaginable timescales. For a black hole, the mass of our sun, the process of leaking this information back out would take longer than the current age of the universe by a factor of trillions upon trillions. It is the slowest, most meticulous evaporation imaginable. Over these immense eons, as the black hole slowly radiates its mass away, it is also painstakingly broadcasting the complete information catalogue of everything it ever consumed. The Hawking radiation is not a featureless hiss. It is a story, the most complex and condensed story in the universe, being told in a language of quantum entanglement, so subtle we are only just beginning to comprehend it. When the final photon leaves the black hole in its last moment of existence, that photon will carry the very last bit of data required to, in principle, reconstruct everything that ever fell in. The book that fell in eons ago could be rebuilt atom by atom. The astronaut's final thoughts, encoded in the quantum state of her neurons, could be perfectly reassembled. There is no loss, there is no deletion. There is only a transformation of state, a temporary storage on a two-dimensional medium, and a near infinitely long playback. The information doesn't just survive, it is returned to the cosmos. Quantum mechanics is vindicated. Its most sacred law holds true even at the maw of infinity. The universe, it turns out, does not have amnesia. Its memory is perfect, and with that, the paradox that threatened to break physics is resolved. Yet the solution leaves us in a world far more bewildering than the one we inhabited before. In saving quantum mechanics, the holographic principle forces us to confront a possibility about our own reality that is almost too profound to accept. If a three-dimensional space like the inside of a black hole can be entirely described by the information on its two-dimensional boundary, could the same be true for our entire universe? Could the three spatial dimensions experience the height, width, and depth of our reality be an illusion, a grand cosmic projection? The theory suggests that it might be. It proposes that our entire universe, all the galaxies, stars, planets, and even you, might be a holographic projection of information encoded on some vast, distant two-dimensional boundary at the edge of the cosmos. We feel like we are moving through a 3D world, but our fundamental reality could be a flat plane of quantum information, and what we perceive as space is an emergent property, a feature of how that information is organized, entangled. It's a staggering thought that the tangible volumetric world around you is a ghost, a hologram generated from a distant lower dimensional reality. Space itself is not fundamental. Time is not fundamental. They are secondary effects pixels on a cosmic screen that create the illusion of depth. The most fundamental constituent of reality is not matter or energy but information. The universe is not a container for things. It is a calculation, a grand processing of information. We set out to solve a puzzle about black holes, and we have arrived at a complete reimagining of existence. The black hole wasn't a paradox to be feared, but a Rosetta Stone. It was a special, simplified case, a cosmic laboratory that allowed us to decipher a deeper truth about the universe as a whole. It taught us that the fabric of spacetime is woven from threads of quantum information, that the laws of gravity are not a description of geometry, but a description of how that information is organized and interacts. This isn't just philosophy. It has profound implications for the future of physics. It connects the world of gravity to the world of quantum mechanics through the shared language of information. It suggests a path forward, a way to unify these two great theories into a single, elegant description of everything, a theory of quantum gravity. The conflict that began with a fire in a cosmic furnace has led to a truce, but a truce that has redrawn the map of the entire universe. We are left staring at our reflection in this new holographic cosmos, and we must ask ourselves a question that cuts to the very core of our being. If we are just projections, if our 3D world is merely a shadow play, then where is the screen? Where is the boundary of our universe upon which the story of everything is written? And who or what is the light that casts the hologram? The resolution of the paradox has not given us final answers. Instead, it has unlocked a door to a universe stranger, more mysterious and more deeply interconnected than we ever dared to imagine. And so the war is over. The long, brutal conflict between gravity and the quantum world, fought in the impossible arena of the event horizon, finds its uneasy truce. What began as a subtle crack in the cosmic ledger, a single piece of information seemingly erased from existence, spiraled into a schism that threatened the very soul of physics. For decades, we stood at a precipice staring into an abyss where the universe's most fundamental laws came to die. A place where something the very essence of what makes a particle unique could become nothing. The paradox was not merely a puzzle, it was an indictment, a charge leveled against our most cherished theories, suggesting that our understanding of reality was profoundly, perhaps fatally flawed. The universe, it seemed, could forget. And if the universe could forget even a single quantum bit, then the predictable causal reality we inhabit was built on a foundation of sand, liable to dissolve into chaos at any moment. Our journey through this intellectual labyrinth has been a voyage into the heart of the impossible. We began in the pristine, silent realm of Einstein's relativity, where gravity was the elegant curvature of spacetime, and black holes were its perfect eternal prisons. They were one-way doors, cosmic dungeons from which nothing, not even a whisper of what fell inside, could ever return. Here, information was not so much lost as it was sequestered, locked away for eternity behind an impenetrable wall of warped geometry. It was a clean, if terrifying picture, but it was incomplete. It was a universe of silent classical giants, deaf to the frantic, shimmering dance of the quantum world. Into this silent majesty stepped Stephen Hawking, who listened closer than anyone before him. He heard a voice where there should have been only silence. He revealed that black holes were not truly black, but glowed with a faint ghostly fire, a thermal whisper now known as Hawking radiation. This was the first shot fired in the war, a quantum rebellion against a classical tyrant. For this radiation, this faint celestial breath, was random thermal and seemingly devoid of any of the intricate data that had been devoured by the singularity. It was the ash of a cosmic fire that had burned the universe's library of information. Suddenly, the sequestered data wasn't just locked away, it was being actively, systematically annihilated. The prison had become an incinerator. The conflict was no longer a philosophical curiosity. It had become a crisis of existence. Quantum mechanics, with its sacred, unbreakable law of conservation of information, stood in stark opposition to the gravitational behemoth that seemed to mock it. The universe could not simultaneously obey both masters. One had to yield. For physicists, this was a moment of profound dread and exhilarating opportunity. The paradox was a signpost pointing directly to the place where our knowledge ended the frontier, where a new, deeper physics had to be born. We followed the brilliant, often bewildering paths forged by minds grappling with this fundamental schism. We saw titans like Gerard and Hooft and Leonard Susskind refusing to surrender the quantum faith, proposing ideas that seemed at first like science fiction. They imagined a universe where the three-dimensional richness of our experience was an illusion, a sophisticated trick of the light. They suggested that the story of everything that falls into a black hole isn't written in the volume of its interior, but is instead meticulously inscribed like a celestial engraving upon the fluctuating surface of its event horizon. This was the birth of the holographic principle, a concept so counterintuitive, so defiant of our everyday perception, that it felt like a desperate gambit. How could a flat, two-dimensional surface possibly contain all the information necessary to describe a complex three-dimensional object, let alone the entire interior of a cosmic monster? It seemed to violate every intuition we have about space and reality itself. Yet this desperate gambit found its champion in Juan Maldacena's breathtaking discovery. His work on string theory provided a concrete mathematical model, a theoretical laboratory where the holographic principle wasn't just a wild idea but a demonstrable fact. Within this model universe, the chaotic, churning physics of a black hole's interior, a world of gravity and warped space-time, had a perfect twin. This twin was a simple, flat system of quantum particles living on its boundary, a system where gravity did not exist at all. Every complex gravitational event on the inside, every particle interaction, every quantum fluctuation had a corresponding calculable event in the quantum field theory on the outer surface. It was a Rosetta Stone for the cosmos. The two descriptions, one with gravity and one without, were mathematically equivalent. They were two different languages describing the exact same reality. And in the language of the boundary, the quantum language information was never ever lost. It was simply shuffled, scrambled, and re-encoded, but its essence was preserved forever. The paradox, it seems, was a misunderstanding born from our limited perspective. We were like an audience member trying to understand a film by looking only at the three-dimensional image projected in the air, without ever realizing that all the true information resides on the two-dimensional film reel running through the projector. The information of a particle falling into a black hole does not vanish down a singularity. Instead, its quantum blueprint is smeared across the event horizon, the boundary of the abyss. As the black hole evaporates via Hawking radiation, that information is slowly, painstakingly released back into the universe, woven into the subtle quantum correlations of the outgoing particles. The universe, it turns out, does not forget. Its memory is perfect. The integrity of quantum mechanics, the bedrock of our understanding of the subatomic world, is preserved. The war ends not with a surrender but with a breathtaking synthesis. But to see this as merely the solution to a thorny problem is to miss the profound revolution it represents. This intellectual siege, this half-century-long struggle with the black hole information paradox, was not a detour in the story of science. It was the main road. The paradox was not a flaw in the universe. It was a gift. It was a cosmic stress test, a crucible designed by nature to force our two greatest theories, general relativity and quantum mechanics, into a confrontation they had long avoided. For most of history, these two pillars of modern physics lived in separate worlds. Relativity governed the grand, silent waltz of planets, stars, and galaxies. Quantum mechanics described the frenetic, uncertain world of particles and fields. They worked perfectly in their own domains, but they spoke fundamentally different languages. The paradox dragged them together into the same impossibly small, impossibly dense arena and forced them to speak. Their clash, which threatened to shatter both, instead forged something new. It revealed that gravity, the force we feel most intimately, might be the grand illusion of the cosmos. It might not be a fundamental force at all, but rather an emergent property, a holographic ghost conjured from a more fundamental reality of quantum fields living on a distant surface. Think of the temperature and pressure of the air in a room. These are not fundamental properties of reality. They are the emergent statistical results of countless microscopic atoms and molecules colliding. We experience the collective effect as a smooth, continuous phenomenon, but the underlying reality is discrete, quantum, and chaotic. The paradox suggests that space-time itself might be like this. The smooth, continuous fabric that Einstein envisioned might be a macroscopic illusion stitched together from a quantum tapestry of entangled information bits living on a boundary somewhere at the edge of space. We fell into the problem of black holes thinking we were studying the nature of gravity, only to emerge with the suspicion that we might not know what space-time or reality itself truly are. This is the enduring legacy of the information paradox. It served as a violent, brilliant catalyst, propelling physics into a new and uncharted territory. It has become the central guiding principle in the search for a unified theory of everything, a theory of quantum gravity. The holographic principle is no longer just a tool for understanding black holes. It is a candidate for the deepest architectural principle of the cosmos. And this is where our journey into the known ends and our speculation about the truly profound begins. For if a black hole, a pocket of space-time, can be entirely described by a lower dimensional surface, what does that say about the universe we inhabit? What does that say about us? The implications are staggering, and they ripple outwards, from the event horizon to touch the very fabric of our perceived reality. We are now forced to ask the most unsettling of questions. Could our entire universe, this vast three-dimensional expanse of galaxies, stars, planets, and people, to be a holographic projection? Could it be that the ultimate reality is not the rich, voluminous space we see around us, but a flat, two-dimensional field of information located on some distant cosmic boundary, perhaps at the edge of the observable universe? Could it be that we, in our perceived three-dimensional glory, are the intricate, emergent phenomena encoded on that cosmic hard drive? This is not just a philosophical game. It is a genuine, albeit speculative possibility being explored at the forefront of theoretical physics. If this were true, it would represent the final step in a long series of cosmic demotions for humanity. We once believed we were at the center of the universe. Copernicus moved us to an orbiting planet. Hubble showed us our galaxy was just one of billions. Now we face the possibility that our very dimensionality is an illusion. Our lives, our thoughts, our entire world could be the holographic expression of quantum bits of information, their complex entanglement giving rise to the illusion of depth, of distance, of gravity itself. Everything we have ever known, every star we have ever seen, every person we have ever loved, could be a projection of a reality that is fundamentally flatter, simpler, and stranger than we can possibly imagine. The universe would not be a great stage, but a great screen, and we are not merely the actors, but the images being projected. This idea reshapes our understanding of the universe's most fundamental properties. Take locality, the common sense notion that an object can only be directly affected by its immediate surroundings. In a holographic universe, this principle is shattered. Two points that appear incredibly far apart in our three-dimensional space could be right next to each other on the underlying two-dimensional surface. A strange, non-local connection could exist between them, a form of entanglement that spans the cosmos. This could provide a new lens through which to view the enduring mystery of quantum entanglement, where two particles can remain connected, mirroring each other's properties instantly across vast distances. In a holographic world, their perceived distance might be an illusion. On the true surface of reality, they might never have been separated at all. Furthermore, this could change how we think about the cosmos itself. The total amount of information the universe can hold might not be proportional to its volume, as we would intuitively expect, but to its surface area. This would imply that there is a finite, calculable limit to the complexity and detail that can exist within our observable horizon. The universe, in a very real sense, might have a limited resolution like a digital image. If we could probe space-time at the smallest possible scales, the so-called Planck length, we might find that the smooth, continuous reality we see dissolves into discrete pixels of information, the fundamental bits from which space-time itself is constructed. Our search for the fundamental constituents of matter might end not with particles or strings, but with pure information. We do not yet know if this holographic vision of the universe is true. It remains a tantalizing, mathematically beautiful idea born from the ashes of a paradox. But it provides us with a new map for exploration, a new set of questions to ask of the night sky. Physicists are now actively looking for ways to test this radical concept. They are searching for signatures of this cosmic pixelation in the faint glow of the cosmic microwave background, the afterglow of the Big Bang. They are designing experiments that could detect a fundamental jitter or blurriness in space-time itself, a sign that our reality is not as smooth and solid as it appears. We are at the very beginning of this new chapter, turning the first page on a story that may redefine our place in the cosmos more profoundly than any discovery that has come before. The black hole, once the symbol of ultimate darkness and ignorance, the point where our theories failed, has become a source of unimaginable light. It has been our reluctant teacher, a gravitational oracle that by threatening to destroy our knowledge forced us to seek a deeper truth. The journey to resolve its paradox has reshaped the landscape of physics, blurring the lines between matter, energy, space, and information. It has left us with a universe that is stranger, more interconnected, and infinitely more mysterious than we ever dared to believe. We are the children of a cosmic hologram star stuff projected from a distant boundary, struggling to read the code from which we ourselves are written. The quest is far from over. In fact, it may have just begun. The black hole information paradox is solved, but in its place stands a greater, more wondrous mystery, the nature of reality itself. And the cosmos, as always, waits for us to ask the next question.